In our attempt to understand the dynamics of life, we create models. And those models are most often based on our understanding of machines. Machines are constructs that are designed to perform a task. They exist near equilibrium, meaning it takes very little energy to maintain their physical structure. They can be reverse engineered so that understanding the parts may get us to understand the whole. And they do not depend on the energy that powers them for their very existence. There are other models. The event model, represented here by a tornado, is one. Tornadoes are events that occur far from equilibrium, combining a variety of forces and elements coming together, self-organizing as a dynamical system that would later disassemble itself into its component parts of wind and water and debris that of themselves seem to have no purpose and lack any semblance of organization. They exist far from equilibrium and require a constant input of energy and cease to exist when that energy dissipates. Reverse engineering is near impossible. We may be able to model a tornado in a bottle, but it is a transient event which requires a continuous input of energy. A bottled tornado doesn't exist. It is an occurrence. But it is useful in helping us understand the intricacies of a tornado. Bioengineers and mechanics have used the machine model and statics and open-chain kinematics in their attempts to model the movement of organisms. They studied the forces on the body as if it were an architectural building fixed in space. Let me introduce you to one of the pioneers in the studies of biodynamics, William P. Lombard, professor of physiology at the University of Michigan. In 1907, he described what has become known as Lombard's paradox. Let's have a go at it. Put one hand on your anterior thigh and your other hand on your posterior thigh. Now stand up. What you have experienced is a co-contraction of what have been considered as antagonistic muscles. To refresh your memory, in standard lever biomechanics, to create movement there is a working muscle, the agonist, and an opposite muscle, the antagonist. When one muscle is working, its opposing muscle is relaxed, and the role of which does what to whom can be reversed. Back to Lombard's paradox. Here, muscles co-contract and work in parallel. There are no agonists and antagonists. Like Schrodinger's cat being both dead and alive, a paradox is a seemingly absurd or self-contradictory statement, and in our world we can think of it as contradicting a paradigm. But wait! That hamstrings and quads co-contract should not have been a surprise to Lombard, who wrote an article on the jumping frog. He replaced the muscles crossing two joints with string, and he found that flexing the hip would create movement in the entire limb in a coordinated jumping pattern that would be occurring in a leaping frog. In the jumping frog, flexion and extension at the hip produce simultaneous flexion and extension of the knee and ankle. Note that the muscles remain isometric, the same length, and isotonic, the same tension. What Lombard was describing but did not quite have a word for it was closed kinematic chain. Then, as it is now, complex biological processes are reduced to simplistic machine models based on levers and open chain two-bar kinematics. In the early 1900s, kinematics was still a new science. It considered motion without consideration of the cause of motion, and introduced concepts like vector, speed, and acceleration, all absent in static lever mechanics. Rouleau's book on machinery of motion set the new standard. Getting back to closed kinematic chain in Lombard's frogs. A closed kinematic chain is a number of links with a minimum of 4, which are connected by joints. The chain becomes a mechanism when one of the links is defined as the fixed link. The mechanism becomes a motor mechanism when one or more links is driven. As an example of how this works, we'll use the pantograph. Although not used much anymore, it was a common device used for copying and enlarging in the art world and in manufacturing. Here you see by copying a small drawing you can enlarge it several fold. Let's break down what's happening. Small movements at one end of the device come out as much larger and faster movements at the other end. In his treatise on motion of animals, Aristotle noted this back even before my time, in 350 BC. The speeding up also has consequences. Kinetic energy, the energy that moves us, is 1/2 mass times velocity squared. And to give you some perspective on this, when the velocity of an object doubles, its kinetic energy quadruples. An automobile traveling at 60 miles an hour has 4 times the impact of an automobile going 30 miles an hour. So now we see what has been described as paradoxical movement in a couple of distantly related vertebrates. Can we still call it paradoxical movement? And what if we also find it in flies and cockroaches and caterpillars, fish of all sizes, shapes, and species, and the locking mechanism of a horse that allows it to sleep standing up, and the cruciate ligaments in the knees of all walking vertebrates, the wrist and forearm in humans, and if you start looking around keeping the 4-bar mechanism in mind, you'll see it everywhere. And with due respect to Tom Myers, who was one of the first to talk in terms of applied dynamics rather than statics, it becomes clear that his muscle trains are open kinematic chains, but if front lines and back lines work in tandem, his anatomy trains function not in series as trains do, but as funiculars that operate as closed kinematic chains in parallel. Here it is at the micro level in intervertebral discs, the mechanics of a virus, and at the molecular level, as in the chair boat flip of cyclohexane. Now, a single paradox challenges a paradigm. Multiple paradoxes require a rethinking of the paradigm, a paradigm shift. What is needed is a new paradigm that make those apparent paradoxes irrelevant. Closed kinematic chains seem to fill the bill, and they're relevant at every scale level. Let me bring you back to something you might have missed on one of the earlier slides. In a closed kinematic chain, for the most part, muscles remain isometric and isotonic, the same length and the same tone. Professor Cleland noted this in 1867, where he noted that muscles often behave as ligaments, meaning they didn't behave as springs, more as tensioners like turnbuckles. They maintained tension in the system, but did not further contract it. Let's get back to making it bigger. Small movements here, and even smaller movements at the start, generate much larger movement at the distal end. The output can be adjusted in various ways, and there are many combinations and permutations of these mechanisms, and they are applicable at any scale. This is Jules from Mechanisms 101. As you can see in this theoretical model, small movements at the spine may be generating much larger movements at the periphery, and locking one bar may lock up the whole system. This points out the role of muscles acting as joint restrictors and not just joint movers. That muscles in the back could be a driving force in body mechanics was touted by my good friend and colleague Serge Grekovetsky in his book The Spinal Engine. His video of a quad amputee shows how the spine is driving the limbs and not the other way around. And the importance of changes in velocity and energy conversion cannot be overestimated. Even relatively small increments of velocity may have profound consequences. Here is Coach Justin from Ultimate Baseball showing how to throw a ball.
It starts from the ground, all right? So all of our momentum, all of our velocity comes from that ground force really driving down through the ground. From there, once we drive through the ground, that works its way, all that energy works its way up the kinetic chain, and then our core, it transfers into our arm, and eventually it goes out of our fingertips when we make the throw. But just the biggest thing is understand that throwing does not come from just all arm, right?
With remarkable insight, Coach Justin got it mostly right. Let's pause a moment here to clear up some confusion. Kinetic chain is a misnomer. Both the so-called open and closed kinetic chains are really kinematic chains. Kinetics deals with analyzing forces acting on an object. Kinematics refers to the geometry of motion, essentially how you design a machine to perform a task. This is the kinetics of Ryan Crouser, Olympic champion, throwing the shot. Our concern here is the weight of the shot and the ground reaction force affect his movement. This is the kinematics of Ryan Crouser, throwing the shot. And here in slow motion, the concern is not the weight he is throwing, but the dance he is doing. Open kinematic chains are based on energy inefficient second and third class lever systems that, instead of taking energy from the ground, are, in theory, powered by muscles internal to the system, a concept that would have Newton turning over in his grave. Open kinematic chains operate in series like falling dominoes, but closed kinematic chains operate synchronously and in parallel, like slats in a Venetian blind. Back to Coach Justin.
Starts from the ground, all right? So all of our momentum, all of our velocity comes from that ground force really driving down through the ground. From there, once we drive through the ground, that works its way, all that energy works its way up the kinetic chain, right? And then our core, it transfers into our arm, and eventually it goes out of our fingertips.
I would suggest that he is describing a closed kinematic chain, taking energy from the ground and throwing it out the hand. This is a Jensen mechanism, a 10-bar closed kinematic chain that the artist Theo Jensen used to walk his strand beasties across the beach. The basic closed kinematic chain mechanism revolves around a central point and is driven by a crank powered by an external force, the wind. Now let's take the basic mechanism and turn it on its head. We can envision the force coming from the ground, sucked up into the center of mass, and thrust out through the arm. Let's do that again. The wind-up and the pitch. Let's listen to Coach Justin one more time.
It starts from the ground, all right? So all of our momentum, all of our velocity comes from that ground force really driving down through the ground. From there, once we drive through the ground, that works its way, all that energy works its way up.
So it's not muscles that powers you. It is the pushback you get from the ground that powers your movement. That energy of movement, kinetic energy, is taken up by the body's springs and is converted to potential energy, where it is stored in those springs. The body's muscle, bone, and fascia are springs, and those springs are the compression springs of bone and the tension springs of muscle and fascia. Since ground reaction force compresses the body, you would think that the initial storage would be in the bone that are also the better springs, as you can see in this graph. The failure to recognize bone as a spring, and quite possibly its most significant spring, robs the body of its major storehouse for potential energy. In a closed kinematic chain and in a tensegrity system, the tension and compression actually work in parallel, so the forces are combined and focused. And that leaves us with somewhat of a confusing picture of muscle. In closed kinematic chains, muscles collaborate, and often muscles act as ligaments, maintaining tension without actually shortening or lengthening. A major role of muscle would be, of course, creating stability. But the driving force of a closed kinematic chain is external to that chain, and something needs to stir it up, like wind or much more likely ground reaction force. As the economist George Box said, all models are wrong, but some models are useful. Now, strand beasties and their component parts are machines, and closed kinematic chains are machines. And coupling them with tensegrity models, they seem ideal for modeling machine mechanics of organisms, and they are far superior to any previous model. As you may have surmised from my earlier comments, I am into tornadoes. Life is an event that occurs far from equilibrium and requires a constant input of energy to sustain it. If you don't believe me, try holding your breath for a few minutes. And here are a few references questioning the machine model. There are many more. So what happens to a machine model in an event world? It is our tornado in a bottle that gives us insights into more complicated events. It is one of those useful models that George Box talks about. It will take time and the involvement of future generations for us to deepen our understanding of life events. Meanwhile, we'll do the best we can.